Welcome back. The last topic was on capacitor, and so we're going to continue with the energy storage element. The second one is the inductor that I'm doing for these sessions. Okay, so inductor and inductor. Okay, an inductor is pretty much formed by a coil of conducting wire. Okay, and it's sort of like, you have a wire and you make it into a coil, right, like this. So therefore the symbol of an inductor or inductance, inductor, okay, is this, what you have seen here, okay, just like this. Okay, please be careful, the sharpened one is your resistor, and make it like a curl is your inductor. Okay, well, an inductor store energy in form of magnetic fields. Okay, sort of like you think of your physics, right? Is it Faraday's law, right? That as your current flows through a wire, it forms the magnetic field around the wire. Remember that? Okay, so something like that. Okay, and when changing in current, when changing in current passing through a coil, then there's a flux linking the coil also changing. Okay, and then changing of flux induce voltage across the coil. In other words, just think of this. You have wire, current flowing through this wire, and then the current that was traveling through it, okay, changes. So therefore, your so-called flux, okay, your magnetic field changes, and then when this magnetic field flux changes, okay, it induces voltage. You have current flowing, the current changes, automatically there's voltage across this coil. That's it. Okay, that's why it's called the inductor. It induces voltage across the coil as you have a changing current passing through it. Magic. Okay, so, well, what about L? Okay, the letter L actually stands for self-inductance. There's another word M, capital M, and that's mutual inductance. You're not learning in this circuit 1 course. I believe it's in the circuit 2. Okay, mutual inductance M. Okay, but this class we just learn self-inductance L. Okay, so the self-inductance is the ability of a coil to establish and induce voltage as a result of a change in its current is called self-inductance. It's like, they induce the voltage by itself in a way, okay, or simple inductance L. The unit is Henry, okay, H, okay, capital H. Okay, well, the dimension, this one we're not going to care much about it, right? In this class, it's physical, terms, like N is number of turns, mu is pretty much the material inside, okay, permeability of the core inside, where the wire is wrapped around. A is the area of the core, okay, L is the length of the core. So it's pretty much like this, like this, right? And this is your L, right? And so this is the area, this area of the core, okay? So, well, we're going to jump right through the voltage and current relationship, okay? Since it says that there must be a changing in the current, so dIdt, okay, to get the voltage induced. So therefore, again, the sign, though you have a current passing through L, right, current going through the positive or negative with the voltage drop, it induces a voltage drop such that this is positive, this is negative as a direction of current going in this direction. And the formula is V equal to L dIdt, okay. So it's not the same with the capacitor. The capacitor, what I equal to C dV dt, okay? So this you remember it as, okay, there must be a current going through to induce voltage. So V, induce V equal to L dIdt. Please remember that too, all right? And so this is a formula to find the current I, okay? So energy storage. Okay, same thing as we did with capacitor, Okay, energy is equal to integration of the power dt, right? P is equal to V times I. So V is equal to L di by dt. So put it here, right? And you get Li square over Z. As Z go from negative infinity to T, substitute Z back, and you get this, assuming that there's no energy stored in the inductor at t equal to minus infinities, okay, at the very beginning. So therefore the formula for energy stored, okay, in the inductor is a half, this is a half Li square, okay, half, okay, Li square. So therefore this is the formula, okay. Well, so this is an example, okay. If you have a current through 1 millihenry inductor, is this, find VL and the energy. So therefore V equal to L di dt. This is L, right? 1 time 10 to the minus 3. Differentiate with respect to T, the current I, the 20 cos 100t, and you get this value for V. And so to find the energy, a half Li square. So a half L, right? And this is your I, your I square, right? Square. So you get this in joules. So please, you have to review your differentiation skill and integration skill also for this. Okay. For the inductor in series, okay, so you add V together, right? V together. So therefore, right, if you have this, okay, right, V equal to, this is the current I plus minus V1 plus minus V2, blah blah blah, right? So KVL, V equal to, right, L total di dt, the same current flowing through it, right? L1 di dt, this is V1, this is V2, plus go on, so on and so on. But the same current flowing through, so you can cancel, they are the same thing. So you're left with L total equal to L1 plus L2 plus L3. Just the same way as you're adding, total resistors in series. Okay, as in for parallel, if you have inductor connected in parallel, right, you have to do these integrations, and let's go to the final answer. The total inductance become L total equal to 1 over L1 plus 1 over L2 plus 1 over L3 to 1 over Ln. So therefore, same thing, same form as in resistors connected in parallel. Okay, so total inductance connected in parallel. Okay, in parallel. Similar to the capacitor, right? Capacitor have a special DC rules. So inductor also has it. Okay, so I'm going to define one of the new term. Okay, transient and steady state. Okay, at this point. Okay, if there's changes in your circuits, there could be some fluctuation in your circuit, right, at one point, and then later on it becomes steady, okay, as the times go on for a long time. So during when your signal is still sort of like not stable, we call it transient time, during the transient, but when it gets sort of like stable, right, we call it the steady state for a long time. Okay, so therefore, for the special rules for the inductor is that, currents through an inductor cannot change, instantaneously. Okay, so therefore I at T0 plus is equal to I at T0 minus. If the switch changes, if your circuit has a switch and switch changes at T equal to 0, okay, switch changes at T equal to 0, we say that I, the current going through the inductor, okay, inductor only, okay, at 0 plus is equal to the current going through inductor at T equal to 0 minus. So this is the case for inductor. Current through an inductor cannot change instantaneously. Okay, and another so-called rules is that, okay, if you look at the formula V equal to L di by dt, right? So the formula indicating that you would obtain the voltage only when there is a changes in the current. So therefore, whenever you have a constant current that go through an inductor, you have a constant current going through an inductor like 5 amp, for example, okay, 5 amps. Well, if you differentiate with respect to T, 5 amps, you get 0, right? So therefore, L d5 dt is equal to 0 volt. So it means that if you have a constant current going through inductor, this is 0 volt. You have current going through, but no voltage drop across that sections. This, we call it, this behaves like, that means your inductor at this particular moment behaves like a short circuit. Short circuit. So please remember that, okay? Okay, an inductor acts like a short circuit if there is no changes in current. So we think that when changes in no current is that, when, for example, a DC current pass through it. Okay, so therefore it would act like a short circuit. Okay, an example, similar example with the capacitor, okay, is, you want to find V at this particular time when IS is given as this graph. Okay, same thing, you divide into your sections like between 0 and 1, from 1 to 2 seconds, from 2 to 3 seconds, and 3 to 4 seconds, and then beyond those two. Okay, and you get and use a formula to find V equal to L di dt. So you find your I, right? So in this portion, the slope is 2 because you change 2 in so-called 1 second. So going up, right? So plus 2, and it crosses the y axis at 0. So therefore, I of t in that section is 2t, right? Between 1 and 2, it's a constant value 2, right? So 2, right? From 2 to 3 seconds, right? It goes down, right? So negative slope from 1 to 3, right? In 1 second, so it's minus 3. The slope is minus 3, right? And you find your y-intercept, okay? So it becomes 8, okay? Okay, so I'm going to say how to find that. Okay, let's say between 2 and 3, right? Now we know the slope is minus 3, right? So therefore, it's like IS equal to minus 3t plus some constant, right? That would cut the y-axis. To do this, to get the value of C, do the substitutions. For example, you can say that, at t equal to 3, right? At t equal to 3, IS is minus 1. So minus 1 equal to minus 3 times 3 plus C. So minus 1 equal to minus 9 plus C. So therefore C is equal to minus 1 plus 9 equal to 8. So therefore your IS is equal to minus 3t plus 8. See, so therefore this is what you get. And when you differentiate all this, is like, di dt is 2, 0, minus 3. And the last portion, you can find it yourself, is this one. So at the end, you'll find out what your V is according to di dt. Okay, you go and look at it. Okay, right, so let's see this example. Okay, given I equal to 3 amperes, so 3 amperes, and given that IL 0 minus equal to 2 amps already, right? Find I1 at 0 minus, IL at 0 plus, and I1 at 0 plus. I1 is right here. So let's take a look. So to start doing this, I would write my circuit, as like a timeline. So at t equal to 0 minus, what does my switch looks like? It opens up, it hasn't closed down. Okay, it's like this. I1 0 minus, IL 0 minus equal to 2 amps. This is R2, this is R1, this is 3 amp, right? So therefore 3 amps comes here, right? and then it's split in here into 2m, so therefore my I10 minus is equal to 3 minus 2 equal to 1 amps. Okay, 1 amps. Okay, then at t equal to 0 plus, t switch closes down, right? Switch closes down like this, right? IL doesn't change instantaneously, so IL0 plus equal to IL0 minus equal to 2 amps. But then I10 plus, if 2 amps comes in here, 2 amps coming in here, right? Right? It would go here, right? Because this is short, right? Doesn't choose to go to somewhere difficult, right? So therefore it goes here. What about IL? IL equal to 2 amp. Goes here, comes here. Oh, come to this section, but this one is short also. So it goes this, this way instead of going through R1. So therefore that's why I10 plus is equal to 0 amps. Okay, so therefore draw your circuit at particular time to get your answer to analyze your circuit. Okay, let's look at this one. Okay, this one I add op-amp into it also. Okay, want to find V out. Okay, so on the op-amp topics, the clip, we have only R resistors, right, connected to it. Now we change to this R to inductor. So using nodal analysis, so op-amp, try to find, use nodal analysis. Look at this. This is VB, right? Ideal op-amp. We still stick to ideal op-amp. The rule for ideal op-amp is what? The voltage at the two legs, the input two legs are equal. Well, this VB is equal to 0 volt because it's connected to ground, right? So therefore, this means VA is also equal to 0 volt. Okay. Current flows from Vs goes here. Of course, there's no current going there due to ideal op-amps, right? So therefore, the current goes up here. Okay, so therefore, this current I1 is equal to ILF. Okay, so this is I1 equal to ILF, right? Like this, right? KCL at A. Okay, now I1, what is the current across I1? It's a voltage drop across R1 over R1, right? The voltage drop across R1 is the potential difference between this point, right? Go positive, negative like this. Positive, subtract the voltage potential at this point. So therefore, Vs, so this is Vs minus Va divided by R1. So this is I1. ILF, the current passing through LF, we have the formula VL equal to L di dt. So therefore, the current IL is the integrations of it, of VL. So therefore, but what is V drop across L in this case? The potential at this point is VA, right? Potential at this point is V out. So subtract it. So VA minus V out. So 1 over LF integrate VA minus V out dt. Well, VA is equal to 0, right? Because we say it's from ideal op-amp characteristic. So VA 0, so Vs over R1 equal to this. And so therefore, right, you want to get rid of the integration, you differentiate both sides. So you differentiate dVs dt, right? When you differentiate with integration, it's gone. LF goes up, right? So therefore, your V out becomes minus LF over R1 dVs dt. So very amazing, no? You differentiate your Vs, the input, to get your V out. It's like a differentiator, okay? Okay, and then inverted also your source to negative values. Okay, so you can try this here also. Okay, try this. Okay, I'm going to give you, you copy this, write it down, find Ix at t equal to 0 minus, t 0 plus, find IL at t equals 0 minus and t equal to 0 plus. Okay, and the switch opens up at t equal to 0. So copy it down. As I said, do it, as time goes by. So what does the circuit looks like at t equal to 0 minus? Switch still closes, right? Switch still closes. So this is your picture, your circuit at t equal to 0 minus. 60 milliamps goes, and then it divided into this current here across 300 ohms, across, divide into Ix, divide into IL, right? Well, also the reason I said IL is a short circuit is because you have to assume that at t equals 0 minus, let's say this is your timeline, right? And this is t equal to 0. And this is like a little bit before t equal to 0 is t equal to 0 minus. And just before, after t is equal to 0 is 0 plus, right? But the circuit, you have to think that the circuit has been connected, like this for a long time, t equal to infinities, until at t equal to 0 minus. If the circuit has been connected like this for a long time, okay, up till t equal to 0 minus, and this is DC, so you would have only DC values, your constant value of current going through all of these branches. So the characteristic, the rules for inductor, right? If you have a constant current going through inductor, it behaves like a short circuit. That's why you draw your inductor like a short circuit like this. So when you have this picture, it's like you have 60 milliamps divided into 3 R's, right? So you can use, if you want to find Ix or IL, you use current dividers formula, right? You use current divider formula, which is this, okay? So Rx, so if you want to find IL is right here. So therefore, it's the same current that's going through 100 ohm. So therefore, your Rx is 100 ohms, right? IL divided from 60 milliamps, right? The source. So 60 milliamp is your I total then, right? Your R total. Well, what does this 60 milliamps divide itself into which R's? So it given itself into this R, 300, 150, 100, and these all 3 R's are connected in parallel. So therefore, your R total is 300 parallel 150 parallel 100 equal to 50 ohms. So therefore, this is your formula for IL. So you get 30 milliamps. Similarly, for Ix, it's just the same thing, simply as that Rx is now 150. So Rx is 150. So your answer is 20 milliamps. So you get this. Then the switch changes, right? Opens up. And this become your, actually let me draw a circuit here. So this become your circuit. The switch, where's the switch, opens up. Right? This opens up like this. So you have, 100. Oh, sorry, I have. Oh, it's okay. Once it's right. 100, right? And I have inductor right here. And I have 150 right here, right? The switch opens here, right? Well, the switch open, it's sort of disconnected this all together. Your answer you want is IL is here, your Ix is here. So is it connect this all together? So that's why I'm drawing only this much here. Okay, you have this. You have this only circuit left to consider because your answer you want to find is only, concern only this group. Well, IL cannot change instantaneously. So IL 0 plus equal to IL 0 minus 30 milliamps. What about Ix? Well, what happened is that now your IL become like a source, right? It's 30 milliamps. So therefore IL flow like this. And it goes through 150 in the opposite direction of Ix. So therefore, Ix 0 plus equal to IL 0 plus equal to this. Get it? So this is how you analyze circuit with switches and inductor and capacitor. All right? So therefore, well, here is, you can do this as a homework here. Pause it. Draw it. This is the answer. No, this is the question. All right, pause your clip. Copy. right? Find I1, find I2, find I3, find IC, find VC at t equal to 0 minus and t equal to 0 plus. So this is 24 volt. Well, I'm going to jump into the answer. Where's the answer? Oh, well, here's the answer. Do it first and then see if you get the same answer or not. All right. Pause it, see the answer. And try to explain to yourself why it's like that. Okay? All right, so this is it for so-called energy storage elements. Thank you. Bye.